Hello, this will be a demonstration of proposition 11 from book 8 of Euclid's Elements, which says that between two square numbers, there is exactly one mean proportional. And furthermore, the square number has to the square number a ratio duplicate of that which its side has to its side. We're given two square numbers, a and b. A and b will both be square numbers. Furthermore, we'll be given their sides c and d respectively, so that c squared, or c times c, makes a, and d squared, that is d times d, makes b. And what we want to prove is that between a and b, there is one mean proportional, such that a is to this number, just as this number is to b. And furthermore, we want to prove that the ratio which a has to b is duplicate that which c has to d. We're going to begin by creating one number. We're going to create the number e. E shall be the product of c and d. It will be the product of the two sides. So c times d makes e. Now, what we have here is the number c multiplied by two numbers to make two other numbers. In this case, c times c makes a. We were given that, c squared makes a. And furthermore, c times d has just made e. And we know from proposition 717 that if a number multiply two numbers and make some products, the products will have the same ratio as the two numbers multiplied. So that c is to d just as a is to e. Now, for the same reason, we can prove that c is to d also just as e is to b, because what we notice is that d has been multiplied by two numbers c and d to make two other numbers e and b respectively. And again, we know from proposition 717 that the numbers multiplied will have the same ratio as the products, so that c is to d just as e is to b. But then, of course, you'll notice we have two ratios which are the same with the same ratio, so property of numbers tells us that they must be the same with one another, so that a is to b just as e is to b. And e is then what we would call a mean proportional, because a is to e just as e is to b. And we notice that there is only one between a and b, so that satisfies the first part of what we wanted to prove. Next, in order to prove that a is to b just as c is to d, we're going to take this proportion a to e just as e is to b, and we'll remember from all the way back in book 5 what exactly the definition of duplicate ratio is, and that definition will carry over for numbers. What that definition said, I believe it was definition 5.9, is that if you have three numbers which are proportional, then the first number is to the third in a ratio duplicate of what the first is to the second. And that definition is going to carry over for numbers, so that because a is to e just as e is to b, our first number a is to our third number b in a ratio duplicate of what our first number a is to our second number e. So a has to be a ratio duplicate of what a has to e. But we know that a is to e just as c is to d. So we can actually substitute this ratio again in by a property of numbers and say that a is to b, or a has to be, a ratio duplicate of what c has to d as well. And this is all we wanted to prove, which means we're done with the proposition, therefore, etc., q, e, d. You know me, I like to give particular examples of what this proposition looks like, so I'll do a few here, actually. 4 and 9 are two square numbers. 4 is equal to 2 squared, and 3 squared is equal to 9. And what this proposition allows us to say is that between 4 and 9, there is some number which we can put between them, such that 4 is to this number, just as this number is to 9. Now, if you follow how exactly we made the number e here, which was the mean proportional between a and b, we take the sides of our two given square numbers and take their product. The side of 4, as it were, is 2, and the side of 9, as it were, is 3. So we take the product of 2 and 3 to get 6. And so we put a 6 in here, and 6 will be our one mean proportional between 4 and 9, because 4 is to 6, just as 6 is to 9. What the second part of this proposition tells us is that if we take 4 and 9 in ratio directly, then their ratio, this ratio of 4 to 9, we duplicate with what 2 is to 3. Because 2 is the side of 4, as it were, and 3 is the side of 9, as it were. Now, what exactly does taking a duplicate ratio mean? Well, you remember from my videos on book 5 and some in book 6, duplicate ratio came up a few times in book 6. Duplicate ratio is just taking the square of the ratio. So 4 is to 9, just as the square of the ratio 2 to 3 is. And what would this mean, taking the square of a ratio? Well, it's taking the square of the numerator and the denominator. So 4 is to 9, just as 2 squared, right, is to 3 squared. And that's easy to verify. 2 squared is 4, 3 squared is 9, 4 is to 9 just as 4 is to 9. Obvious things are obvious. There's a few other examples we could go through. We could go through 4 and 25. So say we wanted to find their mean proportional. What we would do, we would take the side of 4, which in modern terms we would call that the square root of 4, and we would take the side of 25, or the square root of 25. The side of 4 is 2, the side of 25 is 5, 2 times 5 makes 10, so we put a 10 here, and 10 will be our mean proportional between 4 and 25, because 4 is to 10 just as 10 is to 25. Namely, those are both 2 to 5 ratios. And again, we can recognize that 4 is to 25, the exact same as 2 squared, which is the side of 4, is to 5 squared, which is the side of 25. And you can go through this for any 2 square numbers. You can do this with them. That's kind of cool. That's all I've got to say about this proposition, so I'll end the video here and move on to proposition 8.12.